All right.
Correct. I don't know how hard it is to have a drop-off line that says
Drop off, don't park. Whatever. All right. See here. Don't have a quiz yet. That's not posted, but it will be because we'll be finishing this up. This population dynamics for now. Next week's lab, bring your. We're going to use the computer to do our life tables. So if you have a laptop or a tablet and want to do it on there, you can. Could do these life tables by hand. That's fine, but we're going to make our survivorship curves and our mortality curves in Excel. So you're going to have to transfer the data to Excel anyways. And then we'll get back the exams later on. All right. So we left off with population growth. Just kind of going back. We introduced a couple different equations. All right, we introduced this one, discrete non-overlapping generations. It's good when you have things like annual plants where we don't have overlap between our parents and the offspring. They're going to be reproducing, or the parents reproduce, they die, their offspring then reproduce, they die, their offspring reproduce, and so forth. So in that, we're using our lambda. What's the lambda? What was the term for that? Okay, multiplicative growth rate, right? Or what was the other term for it? Finite rate of growth. All right. So to calculate population size, in the future, we have to know our starting population size. We have to know that multiplicative growth rate, lambda, and we have to know how far into the future or how many generations into the future we're trying to predict. Similar equation is this one. This allows overlapping generations, all right, but we've set up discrete cohorts. So we've set up time periods, perhaps for life tables, or we have organisms that reproduce all within a short period of time. What's R? Oh, heck, that's on the slide. It's our net reproductive rate. All right, R naught. Same type of equation. If we were going to predict population size in the future, we have to know our starting population size, we have to know that net reproductive rate, and we have to know how far into the future we are going to predict. All right, and the difference between them is just basically conceptual. All right, same patterns, right? They're both of them are around 1. So if they're equal to 1, we have stasis and no growth. If we're greater than 1, we have growth. If we have less than 1, we have decline. All right? We use them in basically the same way. Change comes when we start talking about continuous growth, overlapping generations. Now what we do is we model population growth using an exponential function. And that exponential function allows us not only to calculate change in population size, which is this dn over dt, but also calculate or predict our population in the future. So for this, we're using R, little r. What is little r? What was the name for that? Malthusian parameter is one. What else? The intrinsic rate of growth. That's probably the one that you'll mostly see, the intrinsic rate of growth. And there's one more. Instantaneous growth rate. So intrinsic rate of growth is probably the one that you'll see most often, followed by the instantaneous growth rate or instantaneous rate of growth. Malthusian parameter, you may see it in historical contexts. All right, but we use it to calculate our change in population size, and our change in population size represents the slope on our population growth curve. So if we went to discrete growth, this is what a discrete population growth curve looks like. Discrete population growth curve looks like. It looks sawtooth. Continuous generations, it's smooth, it's exponential. So our population growth rate, dn over dt, represents the slope. We estimate it using R and our population size. So as population size changes, so does our population growth rate. Our estimate of population size utilizes exponential equation. So we need to know the starting point. What's the population size where we start at? We need to know R, the intrinsic rate of growth, and we have to know how far into the future we are predicting. E is a constant that's in our calculator. All right? E is in our calculator. So we went through and did some examples of these. And there's one more thing to discuss with our exponential growth rate. With our exponential growth rate, we can calculate something called a doubling time. Even with discrete generations, we can calculate doubling time. We can figure out, hey, how fast, how long do we have to wait in order for our population to double? Oh, with discrete generations, we're normally uninterested in that type of question. But here, with exponential growth, we usually are interested in it. All right, as I said, bacteria, yeast are two organisms that can be modeled with our exponential growth curves. And both of those have utility to us. All right, bacteria, yeast, it's used in food production, it's used in medication production. All right, it's used in these things where we need to know population sizes to make our product. Example, beer. Beer needs yeast. We can predict how long it's going to take us to get to a specific population size so that now we can add the yeast to our actual wort and start fermenting. All right, so how do we calculate doubling time? Doubling time is calculated as the natural log of 2 divided by R. This tells us how long it'll take for a population to double in size. And note that it only depends on R. It only depends on the intrinsic rate of growth. It doesn't matter what our population size is. It's the same. Our doubling time for a population is going to be the same whether we have 10 individuals to start or 1,000 individuals to start. The only thing that affects it is our intrinsic rate of growth. So here's an example. We have 2 strains of yeast. Strain 1 exhibits intrinsic rate of growth of 0.2. Strain 2 exhibits an intrinsic rate of growth of 0.3. So what I asked you to do is calculate doubling time for each strain. So what I'll do is start with strain 1 and demonstrate this doubling time. And then we will let you do strain 2. Grab a piece of chalk. So, we're calculating doubling time. All right, and we said doubling time is t equals the natural log of 2 over our intrinsic rate of growth. So for strain 1, we said R is equal to 0.2, which means our doubling time is the natural log of 2 over 0.2, which is what? Natural log of 2 equals, divided by 2, 0.347. So this is probably in hours. Could be like in 8-hour increments, too. But how did I do it on the calculator? Again, it's the natural log of 2, so natural log ln 2 on my calculator. And then I hit equals, get my answer, and then I divide that answer by 2. That's probably the safest. Because if you just type it in, it's a chance that when you do ln 2 and then divide by 0.2, you divide 2 by 0.2 and then take that natural log. So it's probably safer just to calculate the top, get that answer, then divide by 6. So that's strain 1. What's strain 2? Go ahead and calculate it. That 0.347. We're going to fix that. I divided by 2. Fix that. Is that what you got? Why didn't you say anything? 3.466. All right. Yeah, I missed the decimal. So I calculated 2.310. All right. So it's not hard. Natural log of 2 over r, it only depends on whatever that value of r is. So, second question up here is, if strain 1 starts with 1,000 cells and strain 2 starts at 250, which strain will double its population size the soonest? Or, as I have it up here, which strain will have the fastest doubling time? So if strain 1 starts with 1,000 cells, strain 2 starts with 250, which strain will have the fastest doubling time? What do you think? You think strain 1? Who thinks strain 1? Who thinks strain 2? Who thinks strain 2? Just one? Just one person? Why strain 2? Yep. Our doubling time only depends on R. As I said, if we calculate doubling time and say, okay, let's try to calculate doubling time, you're going to be left wondering, where do I put N? You're going to say, I'm given this information, I'm told 1,000 cells. Where do I put that? Is it in the equation? No, doesn't matter. Strain 2 is going to double the fastest. Even at 250. All that you can think about it is this way. To double 250, you only have to get to 500. To double 1,000, you have to get to 2,000. All right? How quickly you get there, it's all dependent on this. Doesn't matter what we start with. Only matters what this is. So, our fastest doubling time, this. Strain 2. Has a higher R, it's going to double in the shortest amount of time. All right. So, this is useful when we're dealing with theoretical growths, or when we're dealing with populations that are just starting out. Because we know, and we said, that we probably have other factors out there that are going to influence our population growth rates. They're going to do things to limit our population size, right? Things like space and resources. So in order for this exponential growth curve to actually apply, we have to meet some assumptions. All right, and there's 5 assumptions that we have to meet in order to use this exponential growth. First up is that we have to have a constant R. This intrinsic rate of growth that we have up here has to stay the same. What does that mean? Well, it means we have no feedback mechanisms. All right, it has no feedback mechanisms, no mechanisms that it will change our birth and death rates as our population sizes change. We have to remain the same. R has to stay the same. You'll see it occasionally as saying, well, we have to have unlimited resources. Yeah, that's true. Because if you don't have unlimited resources, if your resources are limiting, you'll have competition, which then affects your birth and death rates, which then affects your R. So a better assumption than to kind of break it down to say unlimited resources is we need a constant R. R can't change as our population size changes. All right, so that's assumption number 1, constant intrinsic rate of growth. Number 2, no migration. All right, we already made that assumption. We said that first thing we're going to do is assume that net migration is 0. All right, so with no migration, we can say it's a closed population. We defined that term in the market recapture lab, right? Closed population is a population that doesn't have any migration in it. The next 2 assumptions is that we have no genetic structure and no age or size structure. This is also kind of tied to our R, constant R, but with this constant R, we're talking about the entire population. All right, we're talking about the entire population as it changes in size. With the genetic and age structure, we don't want to set up groups of individuals, groups of organisms in our populations that then have different R because of the groups that they form. Or perhaps, so the groups that they form could be like your ecotypes, your genetic, your demes. I guess demes would be a better term. Your demes for the genetic structure, or maybe your ages or the size. So larger individuals grouped together, smaller individuals grouped together. You can't have differences in R between those 2 groups. And in fact, we don't want that type of structure in our population. So with the genetic structure and the age size structure, we're again making this assumption that all of these individuals have the same R, or at least the pattern of change in their R is the same. So maybe their birth potential, their birth rate potential increases up to reproductive maturity and then drops off. As long as every individual has the same pattern, we're good. And then our last assumption, time lags. We can't have time lags between our mating and birthing events. We're modeling an instantaneous change. That instantaneous change says that at this exact moment, this is how our population changes. And the population changes because of births and deaths. We can't look at this and say, at this exact time period, we're going to see some change because we'll have a bunch of births. We can't say that. When we model our population, it has to be instantaneous, which means when we have our births, or when we have our mating and the birthing events, we assume that they occur together. That's why bacteria and yeast are so good, right? They're basically binary fission. Right? You're not mating, we're not having that delay in our development of our embryos until they're born. So there's 5 assumptions. Constant R, no migration, no genetic or age structure, age size structure, and that's 3 and 4, and then no time lags between our birthing and mating events. Question? All right. Summary. We recognize populations change over time. All right? Our future population sizes depend on where we start and then the number of individuals that enter our population through births and immigration, minus those individuals that leave the population because of deaths and emigration. All right, so these are all kind of describing how our populations change and the processes that change our populations. Immigration is assumed to be zero. All right, we assume we're working with closed populations, but we do recognize that immigration is important. Immigration is dispersal. Immigration and emigration is important. This process of dispersal is what connects our populations together. All right, so it not only affects our population sizes through the I and the E, but it affects the similarity, the genetic similarity of our populations. You can have evolution taking a population down its own evolutionary path, but if you have a bunch of dispersal if you have a lot of dispersal bringing individuals to that population, you're going to kind of slow down the selective process. In many cases, you're going to oppose the movement towards a better phenotype. The dispersal is important for these two reasons. And then how do we actually model the populations? Well, it kind of comes down to discrete versus continuous generations. All right, so if we have discrete generations, we do not use the exponential growth equations. All right? Instead, we use lambda and R, big R. Lambda and R naught, that would be good. We have these two equations. Difference is just basically conceptual, and which ones were, is births and deaths included in that lambda or R naught, or is it just births? Right? That's a conceptual difference. How we use it, no difference. If we have continuous generations, now we're using our exponential curves, and we've got two equations that we can use. One tells us the change in population size at a specific point in time, which is our population size, and we can also model our population or predict our population in the future. Related to this continuous generation is the ability to calculate a doubling time. And that doubling time only depends on our intrinsic rate of growth. All right? All right. So, up on our lecture blackboard, turn that off. Underneath problem sets, I have population growth. So, we have a population growth practice problem set. This is for your practice. You work through it. If you don't understand it, or if you're going to check your answers, I have a YouTube video that walks you through how to actually do the problem. All right? When you get through this and you feel pretty good, then you go to the second one, and this is the actual homework. Should have been homework 2. All right? These problems. You got 5 of them. You're going to calculate population sizes. You're going to do it on a separate piece of paper. And then we're going to fix that. What you'll do is click on this. This is the handout. But you don't have enough time to start this assignment and enter in your numbers. And well, you don't have time to start and then do the calculations. So that's why I provide the PDF of all the problems. You can work through it. If you get stumped, go back and work through this problem. Go back and watch these 2 lectures where we work through some of these problems. All right? And if you're still stumped, come talk to me. But this homework 2 is just basically, here's answer boxes, put your answers in. This is homework. All right, so even though it's set up as a quiz, this goes into your homework. This counts as homework points. All right? So you can start working on that. I would not wait. Fix that. I would not wait until the week of our next exam to try to work this out. I would probably go through and work on this first set. There it is, fixed it. I'd probably work on this first set this weekend, since everything is fresh in your mind, and then give it a week and come back to these. All right. So this homework, I didn't set a due date on it. We're going to make it due by that Sunday night before our next exam. So our next exam is November, I want to say 17th, 19th. It's a Friday before Thanksgiving. All right. So I'm going to set the due date for the 14th, by the end of the 14th, so that way I can show the answer key, you can get the answers, and then that gives you Monday, Tuesday, Wednesday, maybe Thursday, to come talk to me if you don't understand how I came up with those answers. All right? We will get that set up. And it's set up as a test, but and you do have 3 attempts, so just in case you mess up entering something in. All right, 14th. There it is. Let's move on. Quiz today. Quiz today, again, in keeping with the Halloween theme of candy. It's the hard candy today. So 5 answer choices. The answers for today are nerds and runts. So I think our choices are nerds, runts, sprees, jawbreakers, and sweet tarts. Nerds and runts. All right, so we just finished other population dynamics. So I'll make the quiz will go live today. We will let it go on Tuesday night, so before our Wednesday class. Give you time to review it over the weekend and on Monday and Tuesday. All right, ready? We made our assumption for the exponential growth that we basically have unlimited resources, constant R, right? Constant R, no age, genetic structure, no time lags, no migration or anything. But we know that that doesn't happen. It's unrealistic out in nature because we do have finite amount of space. We have a finite amount of resources. Can we predict population growth knowing that we have these other factors? And the answer is yes. So what we're going to talk about are the regulatory factors. What regulates our population? And then work with an equation that accounts for these regulatory forces. All right? So we're going to go back to one of these early lectures where we talked about Darwin's theory of natural selection, right? So we said Darwin had 3 tenets to his idea of natural selection. What were they? Give me one of his tenets. What's that? Okay, so we have limited resources. Number 2. Good review. You'll see this on the final exam. It's number 2. No, that's Hardy-Weinberg. Hardy-Weinberg. What's that? Heritable variation exists. Right? Heritable variation exists. So we've got heritable variation exists in our population. We have limited resources. And what's our last one? So because of these two things, because of the heritable variation and the limited resources, competition for resources, those individuals in our population with the variation that allows them to get to those limited resources better than the rest of our population will reproduce and leave more offspring. And thus, we slowly change our population to have individuals with that type of variation, genetic variation. All right, so even Darwin recognized that we do have competition for resources. All right, resources aren't unlimited. And by the extension, he proposed then that selection will favor those individuals that are best able to acquire those limited resources. Now, what's the effect on our population other than movement of evolution? Well, it's going to affect our R. It's going to affect our intrinsic rate of growth. All right? So with unlimited resources, we said that our change in population size, dn over dt, is equal to this little r times our population size. And little r then was defined as our birth minus death rates plus our immigration minus emigration rates. So again, these are all per capita. All right, and we said that this was all constant. If this is true, then our population grows to infinity. But we know that doesn't happen. Our populations are regulated. So as our populations start to become regulated by perhaps our limited resources, then what we're going to see is a change in this intrinsic rate of growth, a change in this R. How does it change? Or why does it change? It changes because we're going to start seeing a change in our birth rates, or our death rates, or our immigration rates, or our emigration rates. All right, so the regulatory factors that are at work are going to produce a change in one or more of these rates, per capita rates, and that has a direct effect on our intrinsic rate of growth, R. All right, now this isn't just competition for limited resources. Our regulatory factors can be abiotic as well. So competition would be our biotic factors. All right, abiotic factors would be like water availability, or maybe disturbances, changes in pH or soil salinity. All right, these things are also going to affect our population. How? Through their effect on birth rates, death rates, immigration, and emigration rates. All right, so these factors, again, by impacting those things that influence R, will thus affect our intrinsic rates of growth. So here's a figure that kind of demonstrates this. We have mortality rates. These are affected by abiotic factors. Drought, all right, say something happened that increases disease. So we've got our drought on both of these. Disease would be more biological functions, biological factors. Food abundance depends on what our food is. Usually it's biological interaction because we're feeding on other organic organisms. All right, but you've got mortality rates. Mortality rates increase as we enter droughts. And then as we come out of the drought, our mortality rates decline. And then when disease comes around, it picks up our mortality rates. So our mortality rate changes through time because of these different factors. But our reproductive rates can also. As we go into a drought, we start inducing stress in our organisms. Stress hormones tend to depress reproductive hormones. So we have a reduction in reproduction during our droughts. And then as we come out of the drought, food abundance increases, our birth rates start to increase accordingly, and then we have our disease, or we have parasites that can come in and, again, take out reproduction. Some of our parasites and some of the structures will actually infect and consume the gonads, so sterilizing the hosts. All right, that's a possibility. Other parasites, they take energy away from our host, and that would have been energy that goes towards reproduction for that host. So together, when we start factoring in both mortality and reproductive rates, then you start seeing this change in population size that might look something like this. So the take-home point of this graph is it's not just biological factors, it's not just abiotic factors that are going to affect our per capita rates, it's everything. We have to account for everything. All right? So let's stop here because we're going to have to pass back these exams. I've already posted the keys. They're outside my office, along with a copy of the exams. Some of you didn't write your name on the actual exam. But you've got copies that are posted, so you can check them out. Also, I have the grade scope part of it. So the front page, that's been released. I didn't realize that you could still see it. Yeah, somebody let me know that they could actually see it on Wednesday. So you can check it out. That tells you what you missed for the different problems. Averages went down a bit. I think I may have told you that it's somewhat typical for the second exam. So what you can do is the grade on here is the total grade. That's what should be reflected in Blackboard. It does not include any of the attendance points. So that column for attendance, add that onto this grade. All right. What we'll do is we will start in the middle. And once you pick it up, you're free to leave. Will Jones. Oh, all right. So anyone that's not, you can stop by my office to pick it up.